This week, we're going to discuss probability distribution. We will focus on two types of distribution, binomial and normal distribution. Here are the learning objectives. By the end of this lecture, you will be able to explain key features of binomial distribution model, calculate probability using the binomial formula, explain the key features of the normal distribution model, as well as calculate the probability using the standard normal distribution table. Now we discuss the details about binomial random variable, which are a special type of discrete random variable. There are some important properties of binomial experiment. First, there are n independent trials which n is fixed. Each trial has two possible outcomes of interest: success versus failure, diabetic versus non-diabetic. The probability of success is constant for all trials and equals p. There's a note for you. The random variable x is number of successes in the n trials. To calculate probabilities, we have to follow the formula. We will see that this is simply going through the process we discussed earlier and putting it in a formula which can be applied for any n and p. The first part of the equation with n choose k is the biggest issue if you don't remember what it is. I have given the translation of the lower right here. On the left of this equation, we have the notation for n choose k that we tend to give in statistics, which is just two big parentheses. Notice there's no fraction line here. It is not n divided by k, it is n choose k, and it means n factorial in the numerator divided by the k factorial times n minus k factorial in the denominator. So we have the probability that random variable x is equal to k is n choose k times p to the k times q to the n minus k, where k is equal to 0, 1, 2, 3 up to n. We need to substitute the value for k, p, q, and n and perform the calculation to get p of x equal to k. Let's look at our example A and B and determine if they represent the binomial experiments. For the example A, we have 8% of all the US adult age 20 plus have diabetes. We will select 5 people from this population at random. Thus, we do have a fixed number of trials, 5. The trials are independent since our population is very large. We only have 2 outcomes, diabetic or not diabetic. And as long as we study this situation over a reasonable time period, it is reasonable that the probability of success is constant at 8%. Therefore, we can consider example A to be a binomial experiment with n equal to 5 and p equal to 0.08. In example B, we have a group of 60 subjects, of which 5 have diabetes. We will select 2 subjects at random. Here there is a fixed number of trials 2, and we only have 2 outcomes, diabetic or not diabetic. However, the trials are not independent since they have a small population sampled without replacement and the population is not constant. It will change for each trial as we have seen when calculating the probability. Thus, in example B, we do not have a binomial experiment. Here we have the list of all possible outcomes for example A, organized by the value of x equals number of diabetes in our sample of 5 individuals. So we have x equal to 0, x equal to 1, through x equal to 5, and we have list that the appropriate outcome for each value of x. We can see that there is one way to get x equal to 0, 5 ways to get x equal to 1, 10 ways to get x equal to 2, 10 ways to get x equal to 3, 5 ways to get x equal to 4, and 1 way to get x equal to 5. In our formula, the n choose k is counting how many ways that particular value of k can happen, and we will see that we will get 1, 5, 10, 10, 5, and 1 in this case. This list is just to convince you of where the value are coming from. For p of x equal to 0, we substitute 0 for k, 5 for n, 0.08 for p, and 0.92 for q. To calculate the 5 choose 0, we have 5 factorial divided by the product of 0 factorial and 5 factorial. We need to be careful. 0 factorial is defined to be 1. All other values are the product of values and all integers are smaller. So 5 factorial is 5 times 4 times 3 times 2 times 1. Here we don't need to calculate 5 factorial since there is 1 in the numerator and 1 in the denominator, which cancel to leave the result of 5 choose 0 equal to 1. In fact, n choose 0 is always equal to 1. There is only one way to get no successes in n trials, regardless of value of n. Then we combine this with the rest of our formula. We have 0.08 to the 0 power. This is equal to 1 and 0.92 to the 5th power. Notice that this is what we found using the multiplication rule, and it's about 0.6591. For p of x equal to 1, we substitute 1 for k, 5 for n, 0.08 for p, and 0.92 for q. To calculate 5 choose 1, I get 5 factorial in the numerator divided by k, which is 1, factorial times n minus k, which is 4, factorial, and when I do these by hands, this is how I will do it. I will write out the numerator as 5 times 4 times 3 times 2 times 1, then write out my denominator as 1 times 4 times 3 times 2 times 1, cancel what I can, and we can get 5 fairly easily. So it is not hard to do by hand. You can also use your calculator if it has the ability to do combinations. Notice we did see that there are 5 ways to have 1 diabetic in our 5 individuals. After multiplying the entire probability calculations, we can get approximately 0.2886. For x equal to 2, we get 5 choose 2 equals 10, and multiplying by the probability, and the calculation gives us around 0.0498. Recall the cumulative probability concept. Cumulative probability is equal to the probability of that value or less. Cumulative probability function lists cumulative probability for all possible outcomes. For example, the probability that x is equal or less than 1 is the sum of probability that x is equal to 0 and the probability of x that is equal to 1. And the probability of x is equal to or less than 2 is equal to the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2. If you want to calculate the probability of x equal to 2, you need to subtract the probability of x equal or less than 1 from the probability that x is equal or less than 2. Finally, we need to discuss the mean and standard deviation of a binomial random variable. The mean of a binomial is very easy to calculate, and we already did this using the logic earlier. If we select 100 individuals from all US adult age 20 plus, where the prevalence of diabetes is 8% in the population, how many would we expect to be diabetic? We said 8% of 100, or 100 times 0.08, which is the n times p, the equation we have here. This does not work with any discrete random variable. It works only for the binomial random variable derived from a binomial experiment. Then we have the formula for the variance, which is n times p times q. But of course, we are most interested in the standard deviation, which is the square root of n times p times q, where q is equal to 1 minus p. In example A, where n is equal to 5 and p is equal to 0.08, the mean is 5 times 0.08, which is 0.4, and the standard deviation is the square root of 5 times 0.08 times 0.92, which is 0.60663. Binomial random variables have many applications in the real-world situation. We need to be able to determine if the binomial distribution is appropriate by verifying the properties. For binomial random variable, we can then find the probability using the equation for p of x equal to k by hand or using the online calculator. And finally, we can calculate the mean and the standard deviation for a binomial random variable using the formula presented here. We have calculated the probability when x is equal to 0 by hand. We can also find the probability using the binomial table. We have the p equal to 0.08 and x equal to 0. Then the probability associated with x equal to 0 and p equal to 0.08 is 0.6591, which is the same as the result calculated by hand. There is another important type of distribution, and that is normal distribution. In general, all normal distributions are symmetric about the mean, which is mu. Unimodal, we could also say bell-curved. The reflection on the curve, where it switches from concave down to concave up, are the mu plus or minus sigma. The equation that provides curve is completely determined by the mean and the standard deviation. Sometimes the notation n, mu, and sigma square is used, but generally we simply provide you with the mean and standard deviation in the problem description. An important special case is the standard normal distribution, which has a mean of 0 and a standard deviation of 1. For normally distributed or approximately normally distributed variable, we can use the standard deviation rule to break up the distribution and determine some percentages within certain range. The standard deviation rules state that approximately 68% of the observations fall within the first standard deviation of the mean. Approximately 95% of the observations fall within 2 standard deviations of the mean. And approximately 99.7% of the observations fall within 3 standard deviations of mean. Standard deviation rule can be rewritten in a probability notation as 0.68 equal to the probability that x is between mu minus sigma and mu plus sigma. 0.95 equal to the probability that x is between mu minus 2 times sigma and mu plus 2 times sigma. And 0.997 equals the probability that x is between mu minus 3 times the sigma and mu plus 3 times sigma. We can use this rule in 2 directions. First, if we know a distribution is roughly normal and we know the mean and standard deviation, then we can determine approximate percentages for a certain range. Second, if we have a data set and we want to know if it is approximately normally distributed, we can determine what percentage fall within 1, 2, and 3 standard deviation and compare those to the target value of 68, 95, and 99.7. To assessing normality, one method is to overlay a normal curve with the same mean and deviation as the sample. The closer the data in the histogram fits is the curve, the closer data are representing a normal distribution. Again, remember the issue of sampling variability. The graph on the left certainly could have come from a distribution with population outlined in the curve. However, the distribution on the right does not seem to match the target curve at all. You might argue that you don't need the curve to make this decision. And if so, likely you're correct. QQ plots, or normal probability plots, are another plot which is commonly used to virtually assess normality. The idea is that if the data are exactly from a normal distribution, the point will fall exactly on the line. Specific type of patterns can be recognized by looking at normal distribution plots. However, we will generally decide the shape of the distribution based upon histogram and box plots, and use the QQ plots only to determine how closely the data resembles a normal distribution. Here are just some examples. The pictures on the left show a normal distribution. The two in the middle shows a negative skew, but as you can see that there are upward curves in the QQ plot. The pictures on the right show a positive skew, and there is a downward curve on the QQ plot. Z-score measures how many standard deviation a value is above or below the mean. Based upon the standard deviation rule, For symmetric distribution, we could use this calculation to determine in which area you fall. For approximately normal distribution, z-score greater than 2 or less than -2 are rare, which will happen approximately 5% of the time. In this way, z-score can also be used to identify potential outliers. The standard normal distribution is an important special case which has a mean of 0 and standard deviation of 1. Thinking back to the standard deviation rule, since the standard deviation is equal to 1, then we can say that approximately 68% of the areas lays between +1 and -1. Approximately 95% of the area lays between +2 and -2. Approximately 99% of the area lays between +3 and -3. You can find the exact probability using the normal table or the online calculators. Any normal distribution can be converted to a standard normal and vice versa using these equations. On the left, we have the conversion from a general normal random variable x to a standard normal random variable z using an equation similar to the z-score equation from Unit 1, except that we have the population mean and population standard deviation instead of those from a sample. On the right, we have the conversion from a z-score back to a general normal random variable x with mean mu and standard deviation of sigma. Normal distributions are commonly used in statistics both as approximation for our sample and as soon we will see an approximation of the distribution of the statistics from a sample. To determine a normal probability when the value does not fall directly on a mu ±1 standard deviation or ±2 standard deviation or ±3 standard deviation landmark, follow these procedures. First, state the problem. Second, standardize the value or z-score. Third, sketch and shape the curve. Fourth, use table B to determine the probability. Here is an example to demonstrate how to calculate a normal probability. So we want to determine the percentage of human gestation that are less than 40 weeks in length. We know that uncomplicated human pregnancy from conceptions of birth is approximately normal distributed with the mu equal to 39 weeks and sigma equal to 2 weeks. A note for you, clinicians measure gestation from the last menstrual period to birth, which adds 2 weeks to the mu. Let X represent human gestation such that X is normally distributed with 39 and 2. The statement of the problem is, what is the probability of X that is equal or less than 40? To standardize, subtract mu and divide by sigma. The z-score tells you how the number of sigma units, the value falls above or below mu. So the third step is to sketch and label axes. And then the last step is use table B or normal probability distribution table to look up the probability of z, which is equal or less than 0.5, and that is 0.6915. Sometimes you need to calculate probability between 2 points. Let A represent the lower boundary and B represent the upper boundary of the range. The probability that Z is between A and B is equal to the probability that Z is equal to or less than B minus the probability of Z is equal to or less than A.